Okay, AP Physics 1, Unit 6/10, Lesson B, which is all on Unit 10 questions on waves and sound. Multiple choice, explained, hopefully. So speakers at rest at the side of the road. Speaker produces, sounds like a Doppler effect question if there ever was one. Speaker produces a steady sound of constant frequency. A student is standing still near the speaker. Two vehicles are driven down the road, a truck approaching the speaker and a car moving away. If the sound is represented by wavefronts, the student and the vehicle drivers each observe a different amount of time between successive fronts. All right, rank the times. Okay, so here's what we want to look at. So here's our speaker with the student next to it. And then the truck is moving towards, make sure I get this right. Yep, truck is approaching it. So we'll say the truck is over here and coming towards, which means it is going to be running into wave fronts more rapidly. So therefore a higher frequency. He's going to hear as he goes, then as opposed to the car, which is moving away, he's going to hear them less frequently. So this will be high frequency. This will be low frequency. This will be in the middle, but the student hears will be somewhere in between them. Now, however, the question is about the times between wavefronts. That's period. That's the time it takes from one crest between crests. So the biggest frequency, since the relationship between period and frequency is a 1 over, the biggest frequency is the shortest period. This will be the middle period, and this will be the longest period. So now some of these symbols here, I don't think they're some sort of typo from the or some sort of side effect of downloading it. So the student should be in the middle. The shorter time should be for the truck. So it should be truck, student, car. So truck, student, car. So I have letter C is my answer. Stationary source emits sound waves of frequency f and wavelength lambda that travel through the air with a speed v. If the frequency of the source is changed to 2f, what will the wavelength and speed of the new wave be? So the speed is a property of the mediums, and it will not change unless you change, the air temperature or something like that. So the speed will remain the same. So right away, I know it's either A or E. And if I double the frequency, since the speed is equal to frequency times wavelength, if this has to stay the same, if I make the frequency go up by a factor of 2, then to keep the same product, I better make the wavelength cut down in half. So it's got to be E. Organ pipe of length L is open at one end and closed at the other. Standing wave of next to lowest frequency, next to lowest, which can exist in this pipe, has a wavelength nearest to. All right, so the open at one end, closed at the other. If that's the case, then this biggest of the smallest amount of a wave, or the biggest wavelength you can have, would have a quarter of a wave as the length of the pipe. But the next to lowest is going to be, for the same pipe, is going to be a half a wavelength and then a quarter. And don't worry if they're not to scale, you get the idea. So the length of the pipe is equal to 3/4 of a wave of the wavelength of, so that makes So the wavelength would be 4/3 L. So for this one, first off, what I want you to know is this, is these two waves, they're going to do funky stuff when they're overlapping each other, but when they get past each other, the triangle will be over here and the square will be over here as if nothing happened. So before they collide, it's this. After they collide is this. So I'm definitely looking for an answer where X is the first thing and Y is the last. So for example, something like either this one or this one, but not this one and not this one. They don't bounce off each other, they just pass through each other. Now the question is, if we get it down to these two, then which one's in the middle? Is it this thing or is it this? Well, I agree this looks kind of funky, but this definitely isn't right. Because when they overlap completely perfectly, the triangle should be on top of the square like that, so I should get something that looks like a house, not something that looks like a teepee. This actually is when, so I'll try to draw this, but when the triangle is, say, here, and the square is here, they'll combine to make this bizarre shape. So the correct answer is going to be XWY. B, I believe. Yes. At a point of observation, the time between successive crests of a passing wave is 0.2 seconds. So they've given us the period, which means you automatically should know the frequency. I just have to do 1 over the period, and that'll give me the frequency. And if I flip 1 over 0.2, then the frequency becomes, I believe that is, comes out to be 5. So 1 over 0.2 is equal to 5 hertz. So for its frequency is 5 hertz. The wavelength, I don't know the wavelength, anything about the wavelength unless I know the speed, and I don't know that. And I don't know where the speed, where they would get the speed from. There's no indication there. That would be a property of the medium. So since I don't know the speed, I don't know any of that. The period isn't 5 seconds. That is the period, 0.2. So frequency, gotta be the right answer. One end of a string is attached to a ring of negligible mass that is free to slide along a pole without friction. A transverse wave pulse is generated at the other end of the string and moves towards the ring as shown above. Properties of the reflected pulse include which of the following? So remember, there's two cases here you should have picked up somewhere along the line. One case is where it's fixed to the end. And if that's the case, the wave that comes in gets reflected and leaves upside down. If, however, it's free to move, like this situation, then the wave that comes in will leave in the same orientation. So I know it's on the same side of the string. I know that's true. It wouldn't move faster. That would be a property of the string, and it's presumably the same tension, so that wouldn't change. Greater amplitude, no, that would mean that somehow the energy went up, and that wouldn't make any sense. So it's got to just be 3 only. Resonance occurs in a soft drink bottle as air is blown across its top. What property of the resonant sound wave in the bottle remains the same as the level of fluid? So what's going to remain the same is the property of the speed of sound. That isn't changed by the size, the depth of the water. Frequency and wavelength are going to get changed in there, but the speed is a property of the temperature of the air. So 1 only. Figure represents 2 guitar strings of different materials and lengths, which are on 2 guitars of different sizes. String 1 is plucked so that it vibrates in the pattern shown. Very soon after string 1 is plucked, string 2, which is a short distance away, vibrates in the pattern shown. The guitars are placed in a sealed chamber and the air is pumped out of the chamber. String 1 is again plucked and vibrates in the pattern shown. Does string 2 again vibrate? Wow, that's a really long question to verify that you understand that sound can't travel through a vacuum, that it has to have something between the string and the other string. So there's got to be air between something between these two strings. So no, because no energy associated with the vibrating string 1 reaches 2 because there's no air to transmit that energy. So D. That is a really long way around to get to that point. They could have basically said, if I pluck a guitar string in a vacuum, do you hear it? And you just be like, no, I get it. That's all they needed to do there. But no, they got to make me read a paragraph. All right. So the wavelengths. So they have two identical situations. The size of the pipes are the same. The depth of the water is the same. But using two different tuning forks, they produce two different waves. They want us to compare the size of the wavelength. So keep in mind that this one's wavelength would go from here to here and would definitely be smaller. X has a smaller wavelength. It's only this long. Whereas this wave, to get a wavelength, I would need a lot bigger computer screen because this is only a quarter of a wave. So I would need 4 times this would be the wavelength. So this one's going to have a huge wavelength compared to this one. So I would expect, if they're going to give this to me, that my expression should tell me that X's wavelength is smaller than Y's. So for example, this is still in the running, this is in the running, this is not, and this is not. Because these tell me that Y's wavelength is somehow smaller. And in order to equal X's, you need to multiply it by 7 or 7/2. No, that's not the case. So I can definitely get it down to these two. Now, let's go with this. What's the factor of difference between the number of waves? In other words, this is a quarter of a wave. How many quarter wavelengths are there in here? Well, this is 1, this is 2, 3, 4, 5, 6, 7. So there are 7 times more quarter waves fit in here than in this has 1 quarter wavelength. This has 7 quarter wavelengths. The factor is going to be a 7, so it's going to be 1/7 in this case. This represents this distance right here. This quarter wave is a 7th of this, which makes sense. All right, last one for this video. A student connects the one end of a string with negligible mass to an oscillator. The other end of the string is passed over a pulley attached to a suspended weight, shown above. The student finds that a standing wave with one antinode is formed along the string when the frequency of the oscillator is f sub 0. So that would be, by the way, a wave that would look like this. Whoops. That would be a standing wave with one section going up and down, one antinode, which is a half a wavelength, right? All right. And that occurs with a frequency of f sub 0. The student then moves the oscillator to shorten the horizontal segment of the string to half of that. At what frequency will a standing wave with one antinode now be formed? Well, you just shrunk the wavelength. So, but the speed's going to stay the same because you haven't changed the weight. So if you made the wavelength shorter, then the frequency should go up. So it should, and if you moved it to half, so it should double the frequency, I would think. So by cutting the wavelength in half, you're going to double the frequency. Why? Because you didn't change the speed of the string. You would have to hung more mass on it or less mass on it, or change the type of string in order to mess with the speed. Since this stays the same, When you moved it in and you create the same shape wave, you've cut the wavelength in half, which means you have to double the frequency in order to keep the same V.